The Ultrafast Dynamics in Matter group is a joint research group between the Institute for Photonics and Nanotechnologies of the National Research Council and the Physics Department of Politecnico di Milano. We are specialized in developing spectroscopic techniques with extreme temporal and spatial resolution and applying them in the studies of ultrafast dynamics in atoms, molecules, and solids. Our activities focus on attosecond science and technologies, high-order harmonic spectroscopy, photoelectron spectroscopy, and ultrafast air spectroscopy.
The generation of attosecond pulses in the X-rays is extremely promising, since it can be used for exploring the behavior of matter with chemical selectivity and ultra-fast temporal resolution. We are currently developing a novel approach that is based on the use of miniaturized microfluidic devices. In this device, we can manipulate the generation conditions on a micrometer scale, and we can significantly improve the brightness of the X-ray pulses.
The high harmonic spectrum generated from a material encodes a direct fingerprint of the electronic structure of the material itself, and the non-linear dynamics triggered by the driving laser field. In our lab, we've developed optical parametric amplifier sources in the mid-infrared for innovative HLG spectroscopy. This technique can be used for probing attosecond electronic dynamics in molecules and structural modifications down to the nanometer scale.
Near-edge X-ray absorption fine structure spectroscopy is a technique founded on the absorption of X-rays by matter and characterized by a core hole in a selected atomic core level. The core hole is filled either by an Auger process or by an electron capture, both of which can be measured in our lab. We excite the sample with a pump beam. Then we probe it with the attosecond XUV pulse, and we look at the probe spectrum in reflection or transmission. This technique allows us to study biologically relevant molecules and semiconducting materials used in solar cells and photovoltaic systems in the attosecond scale.
Photoelectron spectroscopy allows us to measure the energy and momenta of electrons ejected from photoexcited atoms or molecules. In our lab, a velocity map imaging spectrometer, also called VMI, is used to analyze the momentum distribution of electrons produced in the interaction between an ultrafast laser pulse and a cold collimator molecular beam. These studies are paramount for the understanding of photoionization and electron and structural ultrafast dynamics in molecules induced by a pump laser.
Terahertz radiation lies in 100 of micrometer spectral range with a corresponding energy of few tens of milli-electron volts. With such a long wavelength, we have direct and precise access to low energy excitations in materials, such as the carrier dynamics and electron-phonon interaction-related phenomena. For instance, we are studying topological insulators and vial semimetals because of their promising integration in nanoelectronics and spintronic devices. We are also characterizing 2D and 3D perovskite nanocrystal for application in the field of light harvesting and green hydrogen production.
We are participating in the ATOCHEM, interdisciplinary network which is supported by cost action. The main objective is to exploit ultra-short, intense sources operating in the XUV and X-ray spectral regions, and to gain access to the dynamical processes occurring in attoseconds, which is actually the natural timescale for electronic motion in atoms and molecules.
The activities you have seen in this tour are accessible thanks to the impressive advances in laser technology achieved in the last 35 years, which were recently acknowledged with a Nobel Prize to Muru, Strickland and Asking. And lasers allows us to drive matter well beyond its steady-state condition and probe its intimate working mechanism, enabling the understanding of biological, chemical and physical phenomena, as well as the design of novel materials for future countless applications.